Section 3.9 covers the derivatives of exponential and logarithmic functions, and in part 1 we're just going to deal with the exponential functions. An exponential function, real quick, is when we have the variable in the exponent. So the main ones are e to the x and a to the x. A is just any other number, not e. Technically, a could also be e, and it still follows the same idea. So I'm writing these out using the chain rule. So the derivative of e to any function u is itself e to the u times, of course, the derivative of u. Then the derivative of a to the u, such as like 2 to the x or something like that, the derivative of a to the u is a to the u times the natural log of a, the base, times, using the chain rule, the derivative of u. Now this is just a snippet right here of the reference sheet that you have for our class. And if you take a look, they're all on here. So the derivative of e to the x is itself. The derivative of a to the x is a to the x times ln of a, what we just did. Then using the chain rule, we have the derivative of e to a function is the derivative of that function times e to the function. So it's exactly what we have written here. They just use f of x instead of u. But the ideas are the same, so they all are on here. I just wanted to highlight different ways that we can write these derivative rules, either by building the chain rule into it, like I did here, using u, building the chain rule into it using f of x, like they did on your sheet, or not building it in at all. So it just depends on how we write the rule. So these are the two rules that you need to know for exponential functions. We're going to use these rules for e to the something, e to the u, in order to find the derivative here in numbers 1 and 2. So in number 1, we have just a simple function, y equals e to the 2x minus 1, and using our derivative rule, finding the derivative of y with respect to x for e to the something. So e to the u is its own derivative. So we have the derivative of e to the 2x minus 1 is e to the 2x minus 1. Then we need to invoke the chain rule because this function up here, the smaller function, has a derivative other than 1. Its derivative is 2, so we're going to multiply by 2. And to write this more nicely, we want the 2 to be out front, so it's 2 e to the 2x minus 1. And it's as simple as that. E is a very important irrational number. It's actually a transcendental number. It is its own derivative, which is really neat. Let's take a look at number 2. We have a product. We have y equals x squared times e to the 3x squared. So we do need to use the product rule here because each one of our factors of this product has x in it. Let's identify our u, v, u prime, and v prime. Our u here is x squared, and our u prime is 2x. Our v is e to the 3x squared, and our v prime, this is its own derivative. So what I'm going to do is we know that we're going to have e to the 3x squared as part of its own derivative. Then using the chain rule, we need to multiply by the derivative of the exponent here. The derivative of this exponent using the power rule is 6x. So it's going to be 6x e to the 3x squared as its own derivative. Now we can use the product rule, which is u times v prime plus v times u prime. So we have u times v prime, so we're going to have x squared times 6x e to the 3x squared. So we have x squared times 6x, which is 6x cubed, times e to the 3x squared. And of course, this is dy dx. We're taking the derivative now. So that is u times v prime. We just multiplied these two together. Then we're going to multiply v times u prime together. So writing that out, we'll have 2x e to the 3x squared. Now I believe in one of the assignment problems I did ask you to factor. So we are going to be in the next chapter really focusing on working with the derivative and applying it. And so factoring is a big part of that. So to factor this, we can take out the GCF. The GCF is going to be 2x e to the 3x squared. And what we're left with in the first term is 3x squared. And what we're left with in the second term is just a 1. Don't forget that 1, that's a common error students will make, is when the GCF is actually one of your terms, you forget to represent it here. And we didn't need this large of parentheses because it was fairly simple. And so this is our derivative factored. These next three problems are dealing with a to the x. Again, a is just any number that's not e, because any number that's not e is like 2.718 ... Any number that's not that special number has a more particular derivative that we need to write out. E to the x is special because it is just its own derivative. So when we take a look here, we have 2 to the x. So in order to take the derivative of this, dy dx, we use our rule for a to the x. And that rule was it's its own derivative times the natural log of the base, ln 2. Now you can put the 2 in parentheses. A lot of times I don't use parentheses here if it's just one thing that we're taking the natural log of. So you can put parentheses around this 2 if you'd like. Again, I'm just taking the derivative of this first term. And then do I need to use the chain rule? Is what's up here in the exponent, does it have a derivative other than 1? If we multiplied by the derivative of x, it's just times 1. So we don't really need to use the chain rule there because this is just a simple x up here. Then we want to take the derivative of minus 3, which is minus 0. So we don't need to write anything here. So this is our derivative for number 3. In number 4, we want to find dy dt here, taking the derivative of y with respect to t, that's our variable. And we can see that it's 9 to a function. The function is negative 1t. So it's its own derivative. Then we multiply by the natural log of the base, which is 9. Then we take a look up at that function in the exponent up here. And does it have a derivative other than 1? Yes, its derivative is negative 1. So we're going to multiply at the end times negative 1. Now this might be a case where I would probably put parentheses around the 9 just to clearly show that we're only taking the natural log of 9. When we clean up, that negative 1 can go out front, so we can write it as negative 9 to the negative t ln of 9. Then if you want to clean this up even more, because we have a negative t, we can write this as negative ln of 9 over 9 to the t. That negative could also just go out in the very front of this fraction. It could stay in the numerator. We just don't want to write it solely in the denominator. So this is a perfectly acceptable answer right here, pretty much cleaned up. This is also an acceptable answer here. This would not be quite as acceptable because this looks more confusing with the negative 1 at the very end. In number 5, we have 3 raised to a function. So we have, again, a to the u, or a to the x. And in order to find the derivative here, we want to follow our procedure. So I'm going to rewrite the procedure out because this one's a little bit more complex than the other two we've done. So as a reminder, to find the derivative of a to the u with respect to x, it is its own derivative times the natural log of a times, using the chain rule, du dx. So our u value here is tan of x. So for this problem, our u value is the tan of x, and du dx in this case, the derivative of the tangent of x is secant squared of x. So I'm just writing that off to the side just to help me out there for this problem. All right, when we're using this rule, we'll have f prime. So it's its own derivative first, a to the u, so 3 to the tan of x, times the natural log of the base, natural log of 3, times du dx. And in this case, our du dx, I already wrote it out, is secant squared of x. Now this looks kind of complex. I'm going to write, I guess you could just leave it this way. This is totally fine to leave this way, so long as you maybe put the dots here just to show that you're not taking the natural log of the whole thing here. You're only taking the natural log of 3, so it might be a good time to put parentheses, but really they're all kind of complex terms in here, complex factors rather, and so really any order that you write them in is going to look kind of messy, but that is the weird yet correct final derivative here. In number 6, we have an application problem. So we have the spread of a rumor at school is modeled by this function here, r of t, where r of t is the total number of students who have heard the rumor after t days. Okay, let's keep that in our brains here and go to the questions. I rewrote what the function is, r of t. We want to first estimate the initial number of students who heard the rumor. So we'll first work on part A down here. Now, initial number of students means at the very beginning. So that means when time is 0, at the very, very beginning. So the initial number means that time is 0. So it's going to be r of 0. And you will need a calculator for this problem. So just be sure that you are able to use a calculator to plug in 0. So we're going to have e to the 3 minus 2 times 0. So it's just going to be e cubed when we plug in 0 for t. So when we plug that into our calculator, if you are not using the fraction function, be sure that when you divide 100 by the denominator, since the denominator is more than one term, you put it in parentheses. And so we end up getting 4.7. Now, since this is students, we can't have 0.7 of a student, so we're going to round to 5. So we're going to say approximately 5 students initially heard this rumor. Again, this is just a model. And so when we have values like e, we're almost guaranteed to get decimals out because e is an irrational number. It goes on forever. So we are just approximating, and 4.7, because we're dealing with students and we're not dealing with something that can be broken up into decimals, we want to round to the value that makes sense. In part B, we're asked, how fast is this rumor spreading after 2 days? So fast, that's a rate. We want to find the rate of change of our rumor. So we want to find dr dt. We want to find the derivative of this. You can write this in a couple ways. We can write it as dr over dt. R is capitalized because it is over there. Or you can simply write this as r prime of t. So either way is fine. I like how fancy this looks over here, so I'm going to leave it as dr dt. Now we have a quotient, which you don't necessarily need to write as a quotient, but I will here. So we're going to do low d high minus high d low over low squared. So low, part B, so we have low times the derivative of the high. The derivative of 100 is 0, so that goes away, minus high times the derivative of low. All right, so the derivative of the denominator here, the derivative of 1 is just 0, so I don't need to write anything. Then the derivative of this term, e to the 3 minus 2t, is itself times the derivative of this function up here, the exponent. The derivative of this function, 3 minus 2t, with respect to t is negative 2. So we're going to have a negative 2, and I'll just put that out front. All over low squared. So 1 plus e, don't try to actually square this, just write it squared. Perfect. Now let's clean up the numerator a bit. The denominator does not need to be cleaned up. So cleaning up the numerator, this first term goes away because it's times 0. The second term has a negative times a negative, so that's going to end up being a positive 200 here. And then we'll have 200 e to the 3 minus 2t over 1 plus e to the 3 minus 2t quantity squared. And that is our rate of change of the spread of the rumor. It is showing us how the rumor is spreading. So the spread of the rumor, the rate of change of the spread of the rumor with respect to days or time. Now we're asked in part B, how fast is the rumor spreading after 2 days? So we want to plug in 2. So we want to find dr dt at 2. So we're going to plug in 2 everywhere there's a t. So we'll have 200 times e to the 3 minus 2 times 2 all over 1 plus e again to the 3 minus 2 times 2. So 3 minus 4 and then squared. So what I'm going to do is just replace these 3 minus 4s with negative 1 and use my calculator. So let's use our calculator and see what we get. I got 39.322, so 39.3. Now this is students per day. So when we round, we want to round again to the nearest whole number because it's students. So it's about 39 students, and it's a rate. Students hear the rumor per day. dr dt is that rate. That's why I like writing it like this, because it's how r changes with respect to time. So r represents like how many students heard the rumor, and t is in days. So it's 39 students per day. And that is how fast the rumor's spreading after 2 days. Now in part C, we want to know when is the rumor spreading at its maximum rate, and we'll actually find what that maximum rate is. What we can do here is use Desmos or use our graphing calculator, and I kept dr dt here because this is the rumor spreading, and we want to see when it's at its maximum. What I've done here is graphed the derivative function that we found on Desmos. I obviously use x instead of t, although I guess you could use x. In order to get e, what I did is had to go to like the ABC tab down here. So I clicked the ABC button and just used E. Desmos knows what you mean when you plug in E from the keyboard. So if we take a look, we're asked when is the rumor spreading at its maximum rate, and this is how the rumor spreads. And so we found that at day 2, the rumor was spreading about 39 students per day, and that looks about right. It's about 39 right there. And that's actually past the peak of the rumor spreading. The rumor spreading, its maximum point of spread was at day, it looks like about like day 1.5. So we can look in there and see what that actually is. So when we take a look at this top point, it says 1.5 comma 50. So it looks like at day 1.5, it was spreading at its maximum rate of 50 students per day. So we can write that when t equals 1.5, so 1.5 days, that's actually answering the question, when is the rumor spreading at its max rate? If it asks you for what the maximum rate actually was, we can write the rumor was spreading at a rate of 50 students per day. So that's how we can use our calculator to help us find the maximum rate.